All right, welcome back a week or two later. I will show now some other nice operations that we can do using Qibo and in general to give you some idea for quantum algorithms. Okay, so one of the best ideas out there, very nice stuff, is the swap test. Okay, so in the swap test, we have two incoming states, and we can come up with a circuit which will transform those states in some way, but also will take some quantum information from the states, put those states together, actually interfere them together. And then in the output measurements of some assisting qubit on the way, in those outputs of the measurements, we will encode the fidelity, which is just the overlap of two quantum states, okay, two pure quantum states. So that's a way of performing the fidelity. Okay. And I'm not going to discuss the details of it, but you could try to view it as a homework in the slides. You have here an iframe. So you directly have a Wikipedia page here. And I really recommend that you go through the details of this computation here to understand what this circuit is showing. Okay. Well, now the idea is to try it in Qibo. And I will show you one thing that will actually indicate to you how to do quantum compiling and what it might be like to program using circuits or maybe speed up certain circuits and so on, just a vague idea. So in Qibo, normally, if I have the circuit, I would do like add H, the Hadamard on the first qubit. And then what I need is a controlled swap operation. So this kind of gate with those X symbols here is indicating which qubits would be swapping, controlled on the black dot. Okay. And normally in Qibo, I would say control swap and then swap, but it may be in Qibo or not. I didn't actually double check. But what I did instead is to somehow Google about the gate a little bit more, and you find this Stack Exchange page here. And actually, another thing to know is that those gates sometimes have different names. I prefer to use those standardized names telling you what the gate is doing. But basically what happens is that if you have a controlled node, so you are doing the node operation, controlling on two other qubits, okay? And if you have two regular C nodes, then you can have this controlled swap operation, okay? So that's something you can find these days even on Stack Exchange for quantum computing, which is a really good message. All right, so okay, sorry about those shifts. I was checking one thing, and yeah. So now the idea is that normally this controlled swap, I would just pull it from Qibo, but now instead of that, I can put together operations that I already have in Qibo for sure. So this operation I made later add on GitHub. It's actually an open source package. So if I don't do this, you can do this and just add like a few lines implementing this 8x8 matrix, for example, explicitly. But now, never mind, we have a way of doing this in Qibo, and it's a little bit more interesting than just like add controlled swap. No, we will have to add a C node, then we have to add this controlled C node, and then another C node. Okay, so let's try to do this now. For the swap test, I will use two random states. So this is a very brute force way of generating two random states, and they will be called psi2 and psi1. And then my input control state is ket0, which we already know is just a zero state. Okay. And actually, I have to go through everything because I was restarting in the meantime. So as this will be running in a second, I will just keep talking when I reach. Okay. So this will be running now, but now we have the starting point, and now we should start adding stuff. Okay, so I will call this swap test. You see now there's a green tick, so it's finished computing the previous stuff. Circuit on 3 qubits, that's the swap test, okay? And the swap test begins with an Hadamard on the first one, okay? So swap test add gates dot h and at qubit 0, let's see, okay? Then the next thing is that I will actually do it with an error, and then you can think and pause whether you will find the error before I tell you what it is. So we have the CNOT on the first 2 qubits, then gates, it's indicating that I'm not writing correctly, and gates, then Toffoli, it's gate, this gate is called, okay, Toffoli, and then 0, 1, 2 are all of the qubits now, and then again a CNOT, okay? Then I need to add the Hadamard. So basically this block is implementing the picture that we have now. And then there's one more operation, which is another Hadamard. And I need to add a measurement. The way we do a measurement is write M for measurement, and we will be measuring the first qubit. Now, results data, I want to say that this will be swap test on psi 0, 1, 2, and then I can tell it how many shots, how many times to run such a circuit. Physically, that would be the number of repetitions of the experiment. So once you have some remote access through Qibo to some quantum hardware, it will actually physically run the experiment 10,000 times in this case, okay? So let me run this. And actually what will happen, okay, I have some error here. And shots, it's called. But what will happen is that actually I made an error here, okay? So now spoilers, it should be 2, 1 because the order of CNOT actually matters. So the first entry is the qubit that we control, and you see this kind of upside down CNOT here. So we need to do it this way, okay? That's actually something that happened when I was playing with the code, and I had to realize that there's something wrong. So I sampled those random 2 states, and I have 90% fidelity of the overlap, and then I can take an appropriate mean from the samples that I obtained, okay? And then I run this again. The previous number was just from somewhere else, and I got this, okay? So now if I run this again, that should do the trick. I have 90%, and let me run this again, and I have what? 90% again. Now let me do 1,000 shots, and you will see something important about quantum computations is that the error will be increasing. So now 87%, maybe we will get 89 now, okay, but maybe we do it a bit more. Okay, this is almost correct. But I do it a few times, and at some point we will hit maybe 85% and so on. Maybe the first outcome was already quite far away from the mean. But basically we should see that the error will be increasing if we reduce the sample size. So let's see what kind of thing we will sample out. Okay, let me do 100 times. So 92, which is a maybe 2% error. So now 94, which is probably the biggest error that we got away from this 90% so far. Now again 94. So with 100 shots, the numbers will be quite even. So now 6% away from the expected mean and so on. So let's see again, maybe some other random state. Now I should get 97%. Wow. And I got 84%. Wow. Okay. So you could systematize this a little bit more, but just to show you, every time I run this, it will be a different number. So quite often we're quite close. But if you want more digits, you'll have to use more shots. Okay. So if I have more shots, then I have more certainty that I will have more digits correctly. Okay. So let me now override those two states, and let's look at the overlap of the plus state with the zero state, which is a very simple preferred preparation. That's quite easy to do in the lab. We were doing this in Qibo already. So we see, okay, maybe I got this, but if I get 100 shots, maybe it will be a bit less. Okay, 38%. This is pretty bad. Okay, so probably you would need to run more data. 58 is also quite a lot of difference. Let's run this again with 1000. Maybe we get a better result. 52 is a bit closer now. Okay, so you would actually make a loop and maybe make a histogram and check maybe how many shots you need, or just use large deviation bounds. The last remaining two questions is for you to maybe try as a challenge to try to understand the Wikipedia article. All right. Great. I hope I didn't make too many mistakes. Yeah, that's as a recap. Just some ideas how to do the swap test in Qibo. And yeah, you could try to generalize this and try to find papers which explain how to compile the Toffoli gate, because this one we were using as in-house gate. But actually, on a quantum hardware, you would probably have CNOTs earlier than Toffoli. So maybe you want to try to compile Toffoli out of CNOTs. Yeah, some idea what to explore.